Hello everyone, and welcome to the 11th episode of CPP Next. In this episode, we will talk about StudSpan, but we will do it in a different way. We will solve a LeetCode problem using StudSpan. So without further ado, let's start by understanding what is a span. Span is a very simple type that can refer to any continuous container in stud, standard library. That means it's almost the same as stud string view, but for containers that are continuous. And we will see how it's used for our advantage while we are writing our code for this LeetCode question. Now, let's talk about the question in hand. We are given a binary search tree, any binary search tree. It may be balanced or unbalanced, and we are asked to create a function that will balance the binary search tree with the best complexity. To understand how to solve this question, we have to remind ourselves what is a binary search tree. A binary search tree is basically something that arranges number from the root to the leaves. The thing is that those numbers are arranged from left to right. That means if a number is greater than the number that we have in the root, it will go to the right. If we have a number that is lesser than the number in the root, it will go to the left. Let's try and illustrate it with this tree. So let's start with 5. 5 is our root. Then we want to add 4. 4 is lesser than 5, and that means it will go to the left. Then we want to add 7. 7 is greater than 5, and it will go to the right. Then we want to add 6. 6 is greater than 5, it will go to the right, but it is lesser than 7, that means it will go to the left. Then we want to add 2. 2 is lesser than 5, it will go to the left. 2 is also lesser than 4, it will go to the left. And the last one is number 3. 3 is lesser than 5, it's lesser than 4, but it's greater than 2, and that means it will go to the right of 2. And this is our tree. This tree is a balanced tree because the height is just one step further than the other side of the tree. If the tree wasn't balanced, it would look something like this. This is a binary search tree as well. Think about it. 5, then we're going left with 4, then we're going left with 3, then we're going left with 2, and then we're going left with 1. It's still a binary search tree even though it's a list. But we can handle it as a tree. And in our question, this will be the tree that we will handle. Before we start solving the question, we have a few prerequisites that we need to do. For instance, as you remember, the tree is made of nodes. So we have created a node PTR, which is a unique pointer to a node. Then we have the struct itself. It only has a value, left and right, with node PTRs. It has a couple of constructors. Then I have to tell you, I was lazy and I used ChatGPT to create a function that prints a tree. It prints it in a nice way, but it's good enough for us. Then we are creating our tree in hand. So we are creating a list that looks like a tree, with 5 as a root, 4 to the left, 3 to the left, 2 to the left, and 1 to the left. And voila! If we will print the tree, we will get this, root 4, 3, 2, 1. Now we can start solving the question. Now, the first thing we need to do is to use one of the features of the binary search tree. To remind you, there are a couple of traversals that can be used with the binary search tree. And if we will use an in-order traversal, we will get a sorted array. We will use it for our advantage, and we will basically create a sorted array out of it. Now, to understand what's going on here, we need to understand that it's a simple recursive function that runs as in-order functionality and creates a sorted array. So we have the stop functionality of the recursion on line 48. Here we see that if we got to null pointer, that means we need to return. We got to the end of the tree, after the leaves. Afterwards, in line 49, we need to call the function again and to go left because the utmost left leaf is the smallest number. If we got to the smallest number, we need to push it to our new array or vector. And then we need to see if we have something on our right, because there might be something on the right there. If we got to this functionality, we will go to the utmost left leaf again. And that means we will get a sorted array of values. And as you can see, we got a sorted array, exactly what we wanted. The idea behind the next step of the solution uses the fact that we now have a sorted array. If we will take the middle of the array, number 3, that means it will be the root of the new tree. And then we need to process with the functionality the left side and the right side of the tree. If we will go to the left side, we will get 2. If we will go to the right side, we will get 5. Then we need to process what is left from the left tree, and it is 1. And then we need to process what is left with the left tree on the right side, and that is 4. And voila, we have a binary search tree that is actually balanced. And as you can see, we got exactly what we wanted. This is our root. On the right, we have 5. On the left of 5, we have 4. On the left of 3, we have 2. And on the left of 2, we have 1. And the next step will be to explain what exactly we have done with span. So what's going on here? As you can see, it's a recursive function, just like the previous one. This function will stop, or basically we will know if the span is empty. That means we got to the end of the leaves. There are no more leaves, and that means it's a sync. So we are returning null BTR and stopping the recursion. Then we are calculating the middle of the span. This is size divided by 2. Then we need to create a new root from span in the middle. Then we are saying that the root, on the left of the root, we will create a new subtree from a subspan that spans from 0 with m values inside it. And on the right of the root, we are creating a subtree that will be created from a subspan that starts from middle plus 1 and will have size minus m plus 1 values inside it. And again, as you can see, we got exactly what we wanted, a balanced tree. Few things that are important to understand about span. Span is a non-owning view. That means if the vector or something else that is contiguous in the memory will be out of scope and we use span on it, all the memory will be free and we will get a segmentation fault. That means we need to be careful with it. But besides it, look how simple this function is. Instead of writing a function with multiple parameters, we are using slices just like in Java. And in my opinion, if you use it correctly, it's a great way to manipulate and traverse contiguous memory in C++. As always, if you like this episode, like and subscribe, and I will see you in our next adventures.